Hello everyone and welcome back. So in today's video, I want to talk about how the inverse of a matrix can be calculated, and I'm going to talk about how to use the inverse of a matrix to help to solve systems of equations when possible. So the process for finding inverses is to do a row reduction. You start by taking your invertible matrix A, and then you augment the matrix A. You augment it not just with a single vector B, but you augment the matrix A with an entire other matrix, namely with the identity matrix. Then go through and do the full Gauss-Jordan elimination process. Completely convert the matrix A to reduced row echelon form. When you take that matrix and you row reduce it, then A, after being row reduced, is going to transform into the identity on the left-hand side. Because of what we said yesterday in the invertible matrix theorem, if your matrix A is invertible, then when you row reduce it, it can be transformed into the identity matrix. So A on the left side will transform into the identity, and the identity on the right side will transform into A inverse. So let me go ahead and demonstrate that process. Someone says find the inverse of the following invertible matrix A, and its entries are in the first row 2, 1, and in the second row -1, 3. First of all, let's go ahead and confirm that this matrix is invertible. In the case of this small matrix, it would be quite easy to check that just by calculating the determinant. The determinant of this matrix would be 2 times 3 minus 1 times -1, so that would be the number 7. So that's definitely non-zero. So for sure, the question is well posed. This indeed is an invertible matrix. So we will be able to find its inverse. So let me go ahead and take my matrix A on the left side, 2, 1, -1, 3, and let me augment it with the identity matrix of the same size, ones on the diagonal and zeros elsewhere. So now I will row reduce the matrix on the left, turning the matrix on the left into the identity. So one action that I could perform to get started is to swap row 1 and row 2 to just push that value of 1 up into the upper left corner. And then the same action would be performed to the identity matrix on the right. I can now go ahead and add 2 copies of the first row into the second row to cancel out that 2 underneath the pivot. Add 2 times row 1 into row 2. So that will eliminate this 2. That'll give me 7 in this position. That'll give me still a 1 here. And then in the final row, 2 times 1 plus 0 gives me 2. Okay, now let's turn all of the pivots into 1s. So I can multiply row 1 by -1, and I can multiply row 2 by 1 over 7. If I scale the rows in this way, it'll turn both of my pivots into 1. So it's 1 minus 3, 0 minus 1 in the top row, 0, 1, 1/7, 2/7 in the second row. And then almost finished, all I need to do is eliminate these values above the 1 in the second column. So I can do that by adding 3 copies of row 2 up into row number 1. -7/7 plus 6/7, -1/7. Okay, so now we have completed our Gauss-Jordan elimination. The matrix on the left-hand side has been converted into the identity. And what has appeared on the right-hand side is now equal to the inverse of our matrix A. -3/7, -1/7, 1/7, and 2/7. If you like, you can verify that this result is true. You can double check that by multiplying A and its inverse together to see if they quote unquote cancel each other out. If I take the original matrix A on the left-hand side, 2, 1, minus 1, 3, and I multiply it by the matrix A inverse that we just calculated, if I do those dot products, I'll get 6/7 plus 1/7, result 1. I'll get negative 2/7, positive 2/7, result 0. I'll get negative 3/7, positive 3/7, result 0. I'll get plus 1/7 plus 6/7, result 1. So if I multiply the matrices together in that order, I sure do get them to cancel out and become the identity matrix. And if I repeat the process in the other order, always checking both orders, because we remember that in general, when you change the order of matrix multiplication, you can get a different result sometimes. If I do this in the other order, I still get 6/7 plus 1/7, result 1. I get 3/7 minus 3/7, result 0. 2/7 minus 2/7 being 0. 1/7 plus 6/7, result 1. So we have verified that this process in this algorithm has given us the inverse of the matrix A. So now let me demonstrate how matrix inverses can be used to solve matrix equations quickly and easily. For example, let's suppose that we're trying to solve this system of equations, 2x plus y equals 4, negative x plus 3y equals 5. If we write this equation in matrix vector form, we have the coefficients 2, 1, minus 1, 3 getting multiplied by the vector x, y, trying to get me a result of 4, 5. So this would be our coefficient matrix A, this would be our vector x, and this would be our output vector b in the traditional notation of a matrix equation. Now this coefficient matrix A on the left-hand side is exactly the same as the matrix whose inverse we just calculated. So because we have the inverse of the matrix, it is now possible for us to solve this equation by just multiplying both sides of the equation by the inverse here. If on the left-hand side I multiply by A inverse and do the same thing on the right, the A and the A inverse will cancel out. And so I'm left with the solution must be equal to the inverse that I calculated, 3/7, negative 1/7, 1/7, and 2/7. If I go ahead and follow through on that matrix multiplication, the first entry would be 12/7 minus 5/7. The second entry coming from the second dot product would be 4/7 plus 10/7. So after simplifying those fractions, we get 7/7 in the first position and 14/7 in the second position, which simplifies to an answer of 1 and 2. So the solution to this system would have values where the first variable x is equal to 1 and the second component y is equal to 2. So a single unique solution, 1, 2. So this is how matrix inverses can be found, and this is how matrix inverses can be used to solve systems and to solve matrix equations. Now, one of the things that I have observed working with students in this class is that students are very familiar with this process of solving equations using inverses from algebra. So when they realize that matrix equations can be solved using matrix inverses, the familiarity of that idea makes it very appealing to students, and they start to want to use inverses basically whenever they can. But something that I want to draw your attention to is that solving equations using matrix inverses is not quite as useful as it might appear at first. In general, if you're trying to solve a single matrix equation, if you're trying to solve a single system of equations, solving using row reduction is usually the superior method. And there are a couple of reasons for that. So first of all, notice that inverses is not possible at all if your matrix A is not square. If your matrix A is not square, if you're dealing with a coefficient matrix that's rectangular instead of square, then you can't find an inverse at all. It doesn't even make sense to do that. So row reduction is more reliable in the sense that it works both when your matrix is square and when your matrix is not square. Additionally, row reduction is more reliable in the sense that it works even if your matrix is singular. Row reduction can be used when your matrix is singular, and row reduction can be used when your matrix is invertible. So row reduction is a much more reliable and broadly useful method than matrix inversion is when it comes to solving equations. The other thing that I would point out is that, to even find the inverse of a matrix, you usually have to do row reduction anyway, right? So in theory, you're just adding on an entire extra step to the process of first having to do a row reduction to even find the inverse, and then having to follow up and use that inverse to calculate the solution. So you're not necessarily saving yourself any effort doing an inverse instead of doing a row reduction. And not only that, the computer algorithms that have been developed to do row reduction are faster and execute more quickly than the computer algorithms for finding inverses of matrices. And the final sort of problem with matrix inverses is that they are very, very susceptible to rounding errors. Um, just to bring it back to real numbers and to algebra for a moment, if you have two numbers that are very, very small, a small rounding error between these values can balloon to a gigantic rounding error when you take inverses. If you have 0.0000001 and you have 0.0000002, these two values are very, very close together. But when you take their inverse, this small difference becomes a gigantic difference, right? A difference of like a billion units. Small rounding errors in the matrix A can balloon to gigantic rounding errors in A inverse. So that is another weakness of inverses. So if so it might be confusing, right? If matrix inverses have all of these problems and all of these issues, why are we even talking about it, right? Under what circumstances would it actually make sense to use an inverse to do any kind of solution? And so I would say that matrix inverses become useful if you're in a situation where you're dealing with the same matrix A over and over and over again. If you're in a situation where you're using the same matrix A to solve several different matrix equations like AX equals B1, AX equals B2, later on AX equals B3, and so on and so forth. If you're doing this all for the same matrix A, in a context like this, it can be useful to go ahead and find the matrix's inverse if it exists. Because in that case, you're making, in some sense, an investment up front to do the work to calculate the inverse that allows you then to use and reuse that inverse multiple times. But yeah, just a reality check. If you're just solving a single matrix equation and using the matrix A in only one problem, it's usually not worth it to use the inverse. It's usually more effective just to solve the old-fashioned way using row reduction. So because of the weaknesses and drawbacks associated with matrix inverses, what we're going to do over the course of the next two lessons is we're going to work towards something which is called an LU factorization. An LU factorization is a way of rewriting a matrix that allows you to calculate solutions to matrix equations a little bit more quickly. And LU factorization works even when your matrix is not square, and it works sometimes even when your matrix is not invertible. So we'll spend the next 2 days building up that technique to help us in cases where solving using inverses is not viable. So that concludes this video. In this video, we learned the process for calculating the inverse of a matrix when an inverse exists. We saw how that inverse can be used to solve matrix equations. But we noted that solving matrix equations using the inverse is not generally the most reliable or the most efficient method. Solving equations using inverses is generally speaking only worthwhile if you're working on several different problems, all of which involve the exact same coefficient matrix A, in which case finding A inverse acts as a kind of investment work that you do up front to make the subsequent calculations faster.